In this work, we present, from rays to projections, better inputs for feed-forward view synthesis. Given a set of context images, our task is to predict novel view images under target camera parameters. Previous methods adopt absolute valued Plucker ray coordinates to encode camera poses, which causes degraded results on even simple transformations like rotation. Our work instead proposes to use projected point cloud image as direct geometric cues so that the model produces more consistent results. This generalizes to other common transformations, including zooming, world scaling, and stretching. This enables us to drive complex camera motions like dolly zooms while keeping the scene stable and coherent. We further show that a self-supervised cross-view masked autoencoder, trained only to complete masked images, can be rapidly adapted to novel view synthesis thanks to the structural match between masked images and our point cloud projection inputs, and it only takes at least 200 fine-tuning steps to transfer. We now briefly walk through our method pipeline. Start from a few context views. We run off-the-shelf perception models, such as MapAnything, to recover a dense 3D geometry. The recovered point cloud is then rasterized into the target camera to obtain a point cloud projection image. The point cloud image and the context views are split into patches, embedded as tokens, and passed through a transformer-based view synthesis model, and finally predicts the target view. The reconstruction losses are applied to optimize the network. To reduce our dependence on large-scale high-quality 3D data, we propose to pre-train a cross-view masked autoencoder. We randomly mask the ground truth target image to mimic a sparse point cloud projection, and train the network to complete it using the context views. After pre-training, the model is transferred into a view synthesis model by replacing the masked image with our point cloud projection inputs. Without any pre-training, our projective view synthesis model already outperforms the ray-based baseline methods on standard novel view synthesis benchmarks. When we start from the masked autoencoder initialization, the model begins to transfer immediately after just 200 fine-tuning steps. With half the training steps of our baseline, the pre-trained model shows state-of-the-art performances. We now show more qualitative rendering results on novel view synthesis and our consistency benchmark. As can be seen, our baseline model produces notable blocky artifacts while our method is consistent under various camera transformations. This is because these transformation causes a non-uniform, spatially varying perturbations in Plucker coordinates, but only induce smooth and localized changes in the point cloud projection image. We provide a more in-depth analysis in the main paper, please check it out. Here, we apply a transformation to the world coordinate system. Ideally, the rendering results should be unchanged since the camera-scene relationship is not affected no matter how the world gauge is parameterized. However, the absolute Plucker ray coordinates cause degraded results on out-of-distribution transformations. Our projected conditioning instead directly encode the projective relationship between scene and geometry, thus is much more robust to world gauge changes. In summary, we propose to use projective conditioning over traditional ray-based Plucker ray coordinate to encode the camera pose. This brings more consistent renderings, and enables a self-supervised learning framework on uncalibrated video dataset. Thanks for watching.